I hope all of you and your families are finding this difficult time we have to live. My presentation is focusing on how address the end of life of high value equipment in power plants from a sustainable point of view, and how remanufacturing can contribute to improve the lifetime of these facilities. Particularly, my presentation focuses on the renewable energy power plants and more specifically in wind energy. I will present here the latest results of the research that we are currently doing by the UCLM group in the framework of the AUTOREMAN project in collaboration with the University of Birmingham also. After the state of the problem, I will present the framework of the research, the case study, and finally I will show the main results and conclusion of the research. Okay. In this slide, we can analyze the increase of the global renewable energy generation in the world in the last 50 years, with a total generated energy close to 7,000 terawatt per hour by the end of 2019. Hydropower, wind energy, and solar photovoltaic are the three technologies that represent the major share of renewable energy power generation, and China, United States, Germany, India, Japan, Italy, and Spain are the countries with the major renewable energy installed capacity. But many of the renewable energy power generation facilities are at the end of their useful life after more than 20 years of operation, and mainly photovoltaic and wind installations. So the generation of waste in the next year will be very significant. In this graph, we can analyze the projection of the global photovoltaic panel waste from the current photovoltaic power plants in operation. The cumulative panel waste will be close to 8 million of tons by 2030 and 78 million of tons by 2050. In the same way, analyzing the wind power plants currently in operation in the United States and in Spain, we can see the number of wind turbines reaching the end of life that will be higher than 40,000. The 55% of the installed wind turbines in United States and in Spain, close to 12,000, close to 55% that are currently in operation with more than 20 years. All of this in addition of the huge number of wind turbines in the other countries around the world presenting the same condition and the same age. For this reason, taking into account these antecedents, it seems logical to propose alternatives based on the recovery and reuse of components of these wind turbines at the end of their useful life. Three main options we can consider as in-life solution for power plants after several years of operation. First, the dismantling for recycling and disposal. Secondly, the life extension or revamping after a high investment in maintenance to keep the plant under operation and control. Or the third, the repowering combined with remanufacturing in order to reuse, remanufacture, recycling, or disposal of the different components according to the condition and state of them, and the most convenient recovery option from an economic and environmental point of view. The framework is based in the analysis of the closed-loop supply chain. First, this is the direct supply chain of the wind turbine. Main components are manufactured in steel, cast iron, fiberglass, rubber, concrete, aluminum. And once the wind turbine is installed, it operates until the end of life. If we combine the direct supply chain with the reverse supply chain, we obtain a circular or a closed loop supply chain, in this case for the wind power plants, that will be the focus of our presentation. Once the wind turbine reaches the end of life, its lifetime extension could be considered based on the assessment and in situ repair. If the remanufacturing option is decided, the wind turbine is disassembled on site and carried until the facility where the different subsystems and will be disassembled in order to make decision for reuse, remanufacture, or recycling. Reuse, remanufacturing, or recycling. Depending on the state of health and the condition of the components, this could be used as recycled materials, other as reuse and remanufactured components, and other as remanufactured systems or products. Recycling and disposal must be the last use options due to the environmental impact generated in this involved process. We define a model to evaluate the impact of remanufacturing in a wind power plant from a technical and economic point of view. After the data collection and the analysis of the current wind power plant, we propose a technical analysis and an economic analysis. Technical analysis consists of the assessment of the annual energy production, the capacity factor, and the equivalent full lead hours. Economic analysis is based on the evaluation of the main economic parameters showing the profitability of the project. Finally, an stochastic analysis is carried out in order to include the uncertainties that could have an impact in the performance of the remanufactured wind power plant. This is the main expression of the model. And additionally, the model considers the analysis of the uncertainties involved. Technical uncertainties based on the errors in power curve, the shape parameter, and the wind speed. Uncertainties associated with the state of health of the components, based on the consideration about the condition of the components. Each one is considered for reuse, remanufacturing, or recycling, depending on the state. And finally, the uncertainties in the most significant economic parameters, as the electricity price, the inflation rate, the weighted average cost of capital, the maintenance cost of the wind turbines, and of the insurance rate of the wind power plant. And we apply this research to a case study based on a real wind power plant. This is located close to Albacete in Spain. The wind power plant was commissioned in 2001 and has a total of 35 wind turbines close to the end of life. We consider two remanufacturing alternatives or strategies. The first is based on the remanufacturing of the blades, and the second consider the remanufacturing and upgrading of electrical and electronic components. Results reveal significant findings. First, analyzing the improvements in the performance of the improvements in the power performance of the remanufactured wind turbines, we can observe the power performance curves that of the remanufactured components or the remanufacturing wind turbines. The red and yellow are a little better than the original wind turbine. In the same sense, considering the evolution of the annual energy production, the capacity factor, and the equivalent full load hours, we can denote significant improvements in these parameters in front of the original wind turbine. And due to the consideration of the uncertainties in the process, we propose an stochastic analysis based on the Monte Carlo method. This methodology considers the input data are not fixed values, but profitability density functions that defines the random behavior of these variables, depending on the number of uncertainties and the range specified for them, each simulation could involve thousands of recalculations, producing the distribution of possible outcome values. For example, for the strategy 1, we obtain the frequency histogram for the annual energy production and can fit the normal distribution that will be used as input data for the economic analysis. In the same way, we perform the simulation for the most significant economic parameter at the net present value, the discounted profitability ratio, the internal rate of return, and the levelized electricity costs that are evaluated. Results reveal for both remanufacturing strategies the improvements in the performance of the wind power plant and the favorable economic outcomes of these alternatives with enough confidence level. Finally, the conclusion, we could say that remanufacturing can contribute to a more sustainable social, economic, and environmental energy scenario for a better use and improvement of the current renewable energy sources. Remanufacturing is technical and economically viable solution for high-value products that are at the end of their useful life, and the results reveals the impact of uncertainties in the outcomes of the end-of-life strategies, suggesting the use of stochastic approaches to evaluate the performance of the project involving remanufacturing. This is the end of my presentation. Many thanks. If you have questions, I'm open to answer.